Greetings and welcome, friends. Howdy, howdy. Today I've got a little side topic that I want to talk about, giving us some practice with some jumbo and micro numbers. I wombo, you wombo, he, she, wombo. So, but before we do that, I just want to do like a little recall here. If I have 10 to the third and I divide by 10 to the first, what does that become?
10 to the second.
Right, 10 to the 3 minus 1, or 10 to the second. All right, so that's good stuff. So we're going to work with some really big numbers that are numbers representative of things within our universe. Does anyone know, let's see here, throw a little fact at us, the number of atoms in the universe?
10 to the first.
All right, the low estimate is 10 to the 79th power for the number of atoms, so that's 1 with 79 zeros after it. How many atoms would it take for me to write that out on a piece of paper?
A lot.
I don't know. Probably less than that number, I'd hope. And the upper limit is 10 to the 81st. All right. Our friend said 10 to the 80th, which I guess is a pretty good average. Right. You're just like, guys, can't we just compromise and just meet in the middle somewhere? Right. And that's fine. Question, comment?
Isn't the universe always expanding?
True, but the amount of energy is deemed constant, and the amount of matter would also be perceived as constant as well. So it's just spreading out, like too little butter spread over too much toast is what Bilbo Baggins says, something like that.
But what if a lot of people come into the world, like another round of baby boomers?
Right, but that's all made of matter that already exists. Like chances are you're currently breathing an air particle that was also once breathed by Albert Einstein. Or George Washington. Yeah, good stuff. So here's our first question. How much bigger? Or how many times bigger, maybe, is the better way to say it. How many times bigger is 10 to the 81st compared to 10 to the 79th? Well, if I want to compare that in terms of like magnitude, I would just divide them. So 10 to the 81st divided by 10 to the 79th. So how much bigger is that? What do I do with those exponents? Subtract them. 81 minus 79? 10 to the second, which is 100. So it turns out that this universe is 100 times larger than that universe. That means that this universe, all right, could fit like 100 of those universes within it. So they've kind of given themselves a generous margin of error, right? Like it's pretty good, like, you know, they got some breathing room, so to speak. They're like, just in case we're wrong, let's just make it like 100 times bigger than that, just in case, right? So that's the number of atoms in the universe. Good stuff.
I have a question.
Yeah, what's up?
How do we get 100 of the 10 to the second?
Multiply
10 times 10, right?
Oh yeah, silly.
All right, let's consider another fact. All right. How many galaxies are there?
30.
3. That's funny stuff. Funny stuff.
Say 3.
Oh, okay. I thought someone said 3.
I think you said 30.
30. Okay. Yeah, that's far more realistic
Oh,
now.
I thought he was laughing because there were actually only 3 galaxies, and it kind of
No. It turns out that the number of galaxies is 10 to the 11th power. All right. Which is the same as 1 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros after it. So let's see, this is thousands, this would be millions, this would be, it's 100 billion. So 100 billion galaxies. All right, so that's not that bad. So, question, how many atoms per galaxy are there on average?
I guess you take the number of atoms and divide it by 1.
Yeah, sure, absolutely. Right, per, that word means divide, right? Like miles per gallon. How many miles do you get per 1 gallon, hopefully? So the number of atoms, let's use 10 to the 79th perhaps, and divide by 10 to the 11th. So if I divide those, what do I do with those exponents?
Subtract.
Subtract them. So 10 to the 68th is the number of atoms per galaxy, on average. I mean, I imagine some galaxies are bigger than others. Okay. So that's interesting stuff.
Wait. Why don't you do 1068 times, like you did with the other one?
Because I don't want to write 68 zeros after it. Right, that would be, I don't know.
A little too long.
Yeah, I don't know if I'd necessarily have a good grasp on that. You know, that'd be a lot of commas. Well, 68 divided by 3-ish commas anyway. Fact. Let's see. Does anyone know how many planets are in our galaxy?
8.
There should be 9, but there's
Pluto is not a planet.
Well, that's in our system, our solar system.
We have no idea.
I'm really upset that they got rid of Pluto.
Well, the number that they'd discovered is 350 so far. And the way they discover them often is they have to, analyze, gravitational forces on objects in space to see, oh, the sun appears to be having a wobble or something like that, or
Want to hear another cool
all sorts of
fact?
stuff. What's up?
From the time that Pluto was a planet to the time that it wasn't a planet, it didn't even circle the sun once.
Wow, that's crazy.
I
Although, guys, guess what? I was wrong. It's not 350. It's 350 times 10 to the 11th power. Oh, what? I was just wrong by a lot of stuff. Oh, wait a minute. Oh, no.
No, because you said it.
In our galaxy. Right.
All galaxies.
So, yeah, that's what I wanted to do. Total number of planets. Right. So, assuming that some galaxies have more planets than others, yeah, if I wanted to figure out an estimate for the number of planets, I would take the number of planets in our galaxy.
And divide it by 10 to the 11?
Well, I'd multiply
Oh,
by the number of galaxies, I'd imagine. Right. So 350 times 10 to the 11th. Okay. Is what I would end up doing. Which, by the way, is equal to 35. 1, 2, 3, 1, 2, 3, 1, 2, 3. I think I get that right. Did I? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Did I get it? So that's 350 trillion planets, I think. Yeah.
No,
Yeah,
I'm
'cause
pretty
this-
sure that's a billion.
Let's see. 1,000, million, billion. You're right. Good call. 350 billion. Billion. Okay. Interesting stuff. So here's some different, things that we've done with numbers. Here's a weird fact. All right. The probability of a single, let's see if I spell this right, protein, right, molecule forming.
1 in 1 million.
On Earth. We'll narrow it down to just Earth. Over all time Earth existed. So it turns out that is 1 out of 10 to the 161st power.
Wow. Not even a lot.
Is the probability of a single protein molecule forming using all of the atoms of Earth and all of the time that Earth existed. So to give this a scale, imagine, all right, let's rewind back to the concept of how many atoms in the universe, right? If I said 10 to the 79th, right? And if I told you the probability of something was 1 in 10 to the 79th, that would be the equivalent of like me being like, okay, I'm going to go into the universe, all right, I'm going to pick a single atom, and I'm going to like number it or mark it somehow, and then I'm going to send Morrow in like a spacesuit. I'm going to be like, all right, Morrow, I'll give you as much time as you want. I'm going to send you out into space, anywhere in the universe you want, and take as long as you'd like. And you can kind of feel around the different atoms, look at them all. And what's the probability that when you're blindfolded, perhaps, you're out in space in your spacesuit, that you'll find the atom that I picked. All right. So like we'd send him out, and he comes back, and he's like, Mr. Waddy, I think I got it. And I was like, nice try, Morrow. Nice try. Although you weren't even in like the right section of space. In fact, my atom was many, many light years away from the ones that you picked, and that's not even the right kind of atom. I happened to pick, hydrogen or something, right? So that'd be really unlikely. I think you guys would agree. That wouldn't necessarily be a fair game for Morrow to gamble with. I wouldn't recommend he, bets his paycheck on it or nothing. So how much harder is this probability than that?
I would recommend it, because you would take 10 to the 161st and divide it by either 10 to the 79th or 10 to the 81st.
So how much more improbable? All right, so let's take 10 to the 161st, and let's divide that by 10 to the 79th. All right, just for a comparison. All right, what would I do with those exponents? Subtract them. I believe I get 10 to the 82nd, which means, now get this, ready? Imagine the universe, okay? All right, you've got that done. All right, good. You guys are quick. You're very creative individuals. And imagine now we zoom in. All right, we're zooming in on a single atom in the universe. So we've found one atom in the universe, one out of, the 10 to the 79th power of them. And take that atom and replace it with a whole other universe of atoms. Okay? Have you done that? So you've replaced one atom with a whole other universe of atoms, and now do that with every other atom in the original universe. Okay? Because 10 to the 82 is bigger than the number of atoms in our current universe. So 10 to the 161st is the same as if I take every atom in the universe and replace it with its own universe of atoms, marked one, send Morrow out into space to find it, and the probability of him getting that one atom right would have been the probability of this occurring, a single protein molecule forming.
What does the single protein mean?
Proteins are building blocks of life. They're made up of amino acids and used. Eventually, they actually are small machines in our bodies or cells or any living creature that is able to accomplish multiple tasks.
We had this many proteins.
Yeah, we've got a lot of them, if I remember. It turns out, now this number is a little bit negotiable, but the lowest that scientists have settled on is that it takes 239 proteins for life to exist, at minimum.
What did you say?
Okay? So we would need 239 proteins to exist simultaneously in the same location, somehow working together, like they all found each other, and worked together to form, some sort of really simple bacterial life, okay? The probability on Earth, okay, of 239 of them forming is not likely, as you could probably guess. It's 1 out of 10 to the, ready? 119,879th power.
Oh my god.
So that's the same as, 10 with 119,000 zeros after it. Okay, so that's tough. So think about that number. That 239. We have more than 239 proteins in our cells. But for basic life to start, let's consider that. So, but this is just on planet Earth. So let's work with this number and see if we could figure out. Well, that's just planet Earth, but there's a lot of planets. How many planets were there? You guys remember?
350.
Yeah, 350 billion, right? Something like that. Surely that's going to improve our odds a lot, right? Because we only need life to exist on one planet for life to exist. Let's just say, just for sake of math for us, let's just say instead of 350 in our galaxy, that it's 1,000. All right? Just to make the math a little bit nicer, right? So I'm making it like 3 times the size, right? A factor of 3-ish, right? So 1,000 is the same as 10 to the 3rd times 10 to the 11th. So that's the same as 10 to the 14th. So we'll just say we'll round up just to make it real favorable for our calculation. Let's say there's 10 to the 14th planets in the universe, okay? So if I want to figure out the probability
Of going to another planet.
of 239 protein molecules on any planet. Okay, we'll use that 10 to the 14th for the number of planets, and probability says that if I find the probability of one event occurring and I want to find the probability of it occurring multiple times, I can multiply it by the number of times that event occurred. So let's say that I take the 10 to the 14th, the number of planets, multiply by the probability of proteins forming on Earth, 1 out of 10 to the 119,879. Guys, I've got a good feeling about my odds here. This is the same as 10 to the 14th over 10 to the 119,879. What do I do with those exponents?
Subtract.
Subtract them. All right, this is going to put a huge dent in this probability. I like our odds here. 119,865. Wow. So that means it's so much more likely now. However, remember our original fact, this guy right here, was only considering the age of the Earth. So this is the probability of those proteins forming on any planet within the time that Earth has existed. But they say that, the universe is older than Earth. Does anyone know how old the universe is?
Tell us.
Tell us. Okay. They say it's about 13.978 billion years old. BYO. Bring your own universe. BYOU. I like it. Billion years old. We'll call that, I don't know, what do you want to call that? 14 billion years? The way they're able to calculate that is based off of the distance that light has traveled from the furthest galaxies visible, because that's how many years it would take. 14 billion light years away is the furthest that we've seen, and that's how long it would have taken. So we would have seen light further away than that if
Is it possible
the universe was
light
older.
cannot travel farther than
Well, unintruded. I mean, if it's not bouncing off of objects or being absorbed in black holes or different things like that. But that's what they currently perceive. Let's take this 14 billion, which is the same as 1.4 times 10 to the 10th. And I don't like that 1.4. Let's just round it up to 100 billion instead of 14 billion. Are you guys fair with that? So 100 billion. We'll just round up, just to make our numbers nicer. So that's 100 billion years is the same as 10 to the 11th power. Okay. All right. 10 to the 11th. So let's use this and calculate our probability. So I've got what? Let's put another dent in this. So 10 to the 11th. Multiply that by 1 over 10 to the 11. Where are we here? 9854. Oh no, sorry. 119865. My apologies, friends. And what do I do with those exponents? I'm going to subtract them again. So this is going to be the same as 1 over 10 to the 119854. So it didn't really do that much for us here. So this is the probability of 239 protein molecules forming on any of the planets over the life of the universe. Not really good. Let's see if we can figure out a magnitude for this. Let's compare this number to that number of atoms experiment we did earlier. All right, so how unlikely is this? All right. So let's compare this 10 to the 1198. Oh, I dropped a 4 there. Sorry. 854. And let's compare that to the 10 to the 79th. So if I divide that, that's the same as subtracting those 10 to the 119854 minus 79 equals blah, blah, blah. But I want to find out how many times can I divide the number of atoms into this number. I'd want to keep doing this repeatedly until I got down to 0. All right, so I'd divide again by 10 to the 79th, and again, and again, and again, and again. And I'm doing repeated subtraction of these numbers. What mathematical operation is the same as repeated subtraction? Does anyone know? Division, precisely. So let's boil this question down into, let's just take 119854, and we'll divide by 79. And I end up getting this number, 1517.139. Okay?
Do you have this all memorized?
No, I've got it written down here. I didn't memorize all this, please. So now this number, what does this mean? All right, so we've got Morrow. He's going to go searching for an atom in the universe. So imagine the universe, okay? We've zoomed down to a single atom, replaced it with all the atoms of another universe. Now let's say I zoom down within those atoms and replace those atoms with other universes. And I zoom down within those atoms and replace those atoms with other universes. And I do that again and again and again. The number of times I'd have to repeat replacing atoms with universes is this number.
Just to get Earth.
Just to get the number of, or you're saying life on Earth sort of thing, right? Yeah. The life on, or proteins that could form life on a single planet.
And that's only for the smallest planet.
Right, yeah, for the most simple. So that would be highly, highly improbable. But that's just some work with some really large numbers and really small ones. So thanks for watching.
This is